welcome everyone to our regular series of R&D Talks, where R&D experts share some insights into the technological domains that would probably disrupt the industry in the following years. And today is not an exclusion, even though it's the second to last event before a new year. The topic isn't less exciting. So our today's focus would be on energy domain, with specifically on the way how we can apply advanced automated workflows, both for seismic data processing, especially interpretation part, and geomechanical reservoir simulation. How to build those models, how to make them robust, how to increase them efficiency, and what is the current gap in order to make them fully automated, you'll hear and learn today. I encourage everyone to ask the question in the chat or keep them till the end. So we will have like Q&A session where our speaker would be able to answer all of them or most of them, if there will be a lot. But the most exciting, of course, is the speaker of today's event. Let me welcome Peter Popov, who is basically one of our R&D experts with a focus on reservoir simulations, especially geomechanical reservoir simulations. He had a master in applied mathematics and then PhD in aerospace engineering in Texas. After that, working a lot of flows modeling, fluid structure, interaction problems, all together with industrial filtration problems at the academia and industry. But then, since 2011, he has been involved in development of algorithms for solving basically Biot's equation and designing related software for geomechanical reservoir simulations. And today he'll share some of the, I would say, industry insights and his experience within this session. So Peter, welcome, and yeah, please take the stage and have a good session today.
Thank you. Just to add one more thing, almost everything that you will see today is done together with Vladislav Idiev, who is also in the meeting. So this is the agenda. We look at the business case for these things, and then we look at the three processes which are involved in reservoir simulations. You have to interpret the seismic data. You have to create a geological model. Then you have to create a computational model, and then you solve reservoir simulations. I'll briefly describe a little bit more of the complexities of pore-elastic situation, where you have both flow and mechanical deformation. And then there was some work done by SoftServe as well, machine learning, UI, and I'll briefly touch on this as well. So as mentioned, this presentation is prepared for SoftServe, and most of the material here is created either by me or by Vlad Iliev or by both of us. The presentation is transcribed from LaTeX source by Alla Shchekhlova, and the goal is to see what we can do in order to enter the reservoir simulation domain. So, what are the consulting services that we can currently offer? We can do two things at this point. We can offer automated mesh extraction. This is something which basically turns interpreted seismic data into computationally feasible meshes, either for finite elements or for finite volumes. This usually is a quite time-consuming step, and the automated tools we have developed help quite a lot in saving time. The other thing that we can currently do with what we have is we can provide services related to geomechanical reservoir simulations. Most commonly, we can look at caprock integrity, fault reactivation, subsidence, and other things. But these are just two parts of the entire workflow. So basically, what is required to have a fully automated loop is to have seismic interpretation. And seismic interpretations are typically done by geologists, which is very time-consuming job. Typically downstream, after several simulations or several ideas how to place wells and so forth, people come back with to geologists and they require more careful interpretation in this region, or they come to conclusion that the interpretation is not very correct in some other place. So this is an iterative process which need to be done quite often. And at present, it is done entirely manually by geologists. It is very time consuming. This is the one area where machine learning is actually applicable in this domain, in contrast to building the models and solving the equations where it is not. The second step is to construct a geological structural model. This is basically your idea how the subsurface looks, where you have interface boundaries, faults, salt domains, and so forth, and you have to make it into a geologically consistent framework. If you talk to geologists, they will basically tell you that they are telling you a story. 3 million years ago, this happened, then situation developed in this way and that way, and then that happened, and then there was this landslide which created that, and there was that flood which created something else, and so on and so on and so on. So for geologists, these structural models are actually stories, exactly like the children's stories we tell our children. And it makes sense to them. So the model you create has to make sense to the geologists who worked on the initial data. Then you have to make the step from the geological model to a reservoir simulation model. You have to select what part of the model to include and what to not to include. You have to generate grids which are suitable for numerical computations. The grids that the geologists work with usually are not. So you have to do that. And you have to populate with properties, fluid properties, mechanical properties, rock properties. There is a whole list of things that you have to specify before you can run any predictive simulation. And then you run simulations. Once you look at the results, you most likely will have to repeat some part of the process or all of it. And what would really be something novel is if you can integrate all those steps into something seamless, which decreases the amount of manual labor that has to be done. So basically, Vlad and I created a tool which simplifies the construction of the reservoir model, and we also developed a reservoir simulator. Based on the current state of machine learning techniques, what can be done is actually to do the interpretation with some form of it again has to be done by geologists, but with some kind of help from machine learning models, and this would likely radically cut the time required for the whole process. So a few words on seismic interpretation. This is the part that I'm actually not an expert, but I can tell you what the issues are. What you see here on the right, the top gray figure, this is the reflection data from a subsurface scan. So what happens is you get a ship with a lot of microphones which travels through the ocean. It records a lot of seismic traces, basically. There is a source, each microphone records the output, the reflected output. This whole thing is processed into something which you see on the top figure, and this is the spatial locations of each reflection that was observed and the intensity of the reflection. So the goal from having this data, you can call this the primary data, The goal is to A, compute the wave speeds. There are at least two in the isotropic case, there are two wave speeds, pressure and shear waves. So based on the time lag between different reflections, you can actually figure to some extent what is the speed of sound in that particular area, and then you do it all over the place. It is a complex inversion problem. The next thing you have to do is you have to extract horizons. The interface boundaries that you see on the second picture to the right are horizons. Horizons are layers where geological layers change from one to another. Typically, these layers are there because something happened. For example, there was a flood, or there was an earthquake, or there was a landslide from somewhere, and so forth and so forth. On this picture again, you also see two folds. There is one fold here and one fold here. Folds typically happen when the crust moves up or down, and since it moves unevenly, at some point, some part of the formation will break from the other, and you get this type of fold discontinuities. They are essential because they can either serve as a fluid transmission area. Basically, for example, everything that comes here will immediately get transported all across. Or they can alternatively be completely sealed with some kind of mud or something like that. And in that case, they completely compartmentalize your reservoir. What you see on this figure actually are the rock type indices. This was converted to several types. This is actually part of a data set which was used as a machine learning challenge to see if it is feasible to use such techniques to recover rock types, horizons, faults, etc. The answer is qualified yes. With the help of geologists, you can do it. So this is the part where we don't have that much expertise. What I'm going to focus is the second part, which is once you have this kind of indicator cubes, how to extract the computational meshes, and then I'll talk about actual reservoir simulations. So the intuitive idea is to put some grid, some regular grid. So let's say you have some indicator cube. Let's say if you have one, it is, for example, salt formation. If you have zero, it is regular rock type. It can be anything. It can be salt, turbidite layers, particular rock type, anything else. The traditional way this is done is you put a regular tetrahedral grid on this thing, and then you just connect level set surfaces. The figure on the top right shows why this is generally wrong. Here you have some indicator cube. These are the values. You're interested in extracting some particular level set, for example, this level surface. If you put an underlying grid, this is in 2D, which is oriented correctly, then you will pick it up. But if instead of this triangular grid, you put alternative one, which is just as presumptuous as the first one, then your interpretation is wrong. So what we decided to do was to use trilinear interpolation in 3D in order to truthfully represent level sets that arise from indicator cubes, rock facies, and so forth. This turned out to be a multi-year exercise, which turned out to be quite complex. When you start it, you expect that generally, if you have some function, basically you have a function which is defined at the 4 vertices here and the 4 vertices below. You do linear interpolation in each direction, so this makes the whole thing trilinear. The intuitive idea is that you'll get the level sets of this function will be something like that. Let's say you have 4 points. It will be some kind of rectangle, some kind of triangle, or something like that. It turned out that there can be a lot of really weird shapes and we had to account for each one of them topologically so we can construct correct level sets. And correct is essential because what you want is you want your eventual surface reconstruction to be watertight. You don't want holes, you don't want self-intersections. And once you start to do such things in the naive way, then you're going to get both. You're going to get holes. This here will be a hole, and there will be self-intersections. So these are some examples of how weird the level sets on trilinear functions can look like. We ended up generating almost all possible variants, and we designed code to handle each one of them separately. They actually split into several classes. So the end result of this is this movie. I have no idea what Polygonica is. Fortunately, it doesn't play in PowerPoint, so I'll play it here. This is a Gulf of Mexico salt, which is interpreted on in an indicator cube and then converted to surface volume. So what you see initially, these are individual slices of the data, and this is what geologists actually generate. So they start to look at the data. They don't do every slice. They usually do every 20th or every 50th slide. But they look at a 2D picture. They look at the shape, the velocities, and they connect points to create a surface. Luckily for faults, the salt has a salt actually acts as a incompressible fluid with a very high viscosity, and it has a very specific velocity, sound velocity. So you can quite quickly pick up salt from the pressure velocity. So this is the eventual mesh that you generate from that indicator cube, and it is regular enough with good enough aspect ratio that you can actually do computations with it. So the next topic is what do you do? And just to make the point, this can be salt, it can be reservoir layers, it can be other type of inclusions. So having the ability to mesh this thing can shave off several months of work when you construct the actual simulation model. Next topic is reservoir simulations. So basically, what is the purpose of reservoir simulations? What you want is you want to predict the movement of fluids in the rock as you drill wells, and you either produce what is inside or you inject something into the rock so that it is either stored there or you use it to push what is inside. Basically, oil reservoir is contrary to the wording. This is not a big hole with oil in the ground. This is porous rock with porosity somewhere in the range of 10 to 30%. And the fluids are inside. So getting them out is essentially the same process as trying to get out water from a kitchen sponge. You unless you squeeze the sponge, the water is not going to go out. So you either has to compress it or you have to push some other fluid to push the water out. With oil, it is the same. Usually, these reservoirs are pressurized. When you drill a hole, some part of the fluid will go out, but this is usually something small, like 3 to 5% of the oil will just go out by itself. Everything else you need to get out by drilling additional wells and pushing water or CO2 or some other fluid so that it displaces your oil and it goes out through the original well. And how to actually do that can be quite complex depending on geology, material properties, and so forth. So this is the purpose of doing reservoir simulations. You put some wells in the model, you try some scheme to produce and to inject, you change it until you get something which reasonably maximizes the output you're going to get out of a field. How do you do that? You have to solve numerically the PDEs which describe the appropriate reservoir. And these PDEs can be variation of one or several things, but what they always invariably include is diffusive flow in highly heterogeneous media. Other than that, the other issues that you have to address are how many fluids do you have. Typically, you have at least two. One would be water, one would be oil. Just a note, you always have water inside the ground. I mean, always. So it is a completely ideal situation to imagine something where you have only single phase. This is not likely. So as a start, you have at least two phases. Depending what you inject, you can still have two phases, so you can get more. The oil by itself usually has dissolved gas. So once you start changing the pressure, what usually transpires is that if you decrease the pressure, gas will bubble out of the oil phase. So from two you go to three phases. The next issue that you have to address is what kind of grids are you working with. You can either work with structured with typical finite element, finite volume grids which are used in industry, which is not the typical case. So you can use unstructured grids which you generated the way we showed earlier. And the more typical cases, you use structured corner point grids, which follow closely the geology, but because they're unsuitable for direct computations, you have to do a lot of work in modifying your numerical schemes so that they can work in such situations. These are usually referred to as corner point grids. You have to also worry whether your different fluids mix with each other or they don't mix. You have to worry additionally if you have highly heterogeneous permeability, which is quite often the case. You can also, and this is what we were doing, you can see what will happen if your reservoir, as your reservoir is produced, you account for the fluid flow and for mechanical deformations. Again, depending on the situations in which you produce the field, you may have thermal flows. And you may have chemical reactions between the phases. So depending on what you do, you have one or different version of a system of partial differential equations. Some of them elliptic, some of them hyperbolic. And yeah, so what you do really depends on the physics of the problem. Why do you want to do that? You may want to, I mean, other than production, other than how to organize your production, there are plenty of other reasons why you want to do reservoir simulations. The initial pressure in the field is extremely important for the drilling process. Depending on how the pressure is distributed, when you start drilling, you might drill successfully, you might lose your equipment, or the whole well might actually blow up and you get issues on the ground. So characterizing the initial pressure is essential for the initial phase of drilling. How do you do that? You have to basically compute the stress state. So basically your initial pressure will tell you what is the stress state of the rock, and from there you can have some idea what well trajectories will break it and what well trajectories will not break the rock. In addition to that, you also figure what kind of drilling fluids you have to use. I mean, the way you play with it is based on the stress state in some area. You start the drilling process, you're going to put either more dense or less dense fluid. That means water with more mud or with less mud. And the more mud you have, the more weight your fluid has. So it is going to act differently depending on what the stress state is. Third bullet, which is bolded, is of course how the fluids will flow. In addition, you may want to evaluate if, for example, injecting certain gases or fluids will stress the reservoir to the point where you break the rock, which keeps the oil in place. Basically, in order to have a reservoir, the top part of your reservoir should be impermeable rock. Oil is less dense than water, so unless there is something to stop it, it will, over geological time, bubble out to the surface. So in order not to bubble out, you need to have some impermeable layer which keeps it in place. As you produce the reservoir, you might easily stress it and break it. And if there are nearby faults in place, then your oil will very quickly reach the sea floor, which is not desirable. Again, based on the mechanical state of the reservoir, you may or may not reactivate existing faults. And already mentioned drilling places, time, schedules, and so forth. How are reservoir simulations performed? There are roughly two different type of methods which are suitable. One is self-centered, finite volumes. The other option is mixed or hybrid finite elements. Each of them have their own strengths and weaknesses. In addition to that, depending on what your permeability field is, mostly your permeability, but also elastic properties, you might have to do one form or another of multi-grid or domain decomposition, or alternatively homogenization theory. So these are basically the tools that you need in order to design reasonable reservoir simulation. I will stress again that neither present day nor future machine learning techniques are remotely suitable to solve this problem. Not just solving porous media, but PDs in general. There are several simulators which are industry accepted. The earliest one is Eclipse by Schlumberger. They pioneered corner point grids with special discretizations on finite volumes that would account for discontinuities along faults, horizons, and so forth. In addition, they also have reservoir simulator which uses geomechanics in some basic way. There is another one called T-Navigator, which is quite popular for fast computations of relatively simple models on GPUs. Schlumberger also designed a reservoir simulator. Actually, it was designed by Schlumberger on request from Chevron, which uses unstructured finite element grids. And if you have really, really complex compositional models, compositional models are the case where you have several different fluids and they are highly miscible. So one component goes into several phases and so forth. Usually the simulator of choice is done by the computing modeling group, CMG. So they probably have the best compositional simulator. What we do is multi-phase geomechanical reservoir simulation. where we emphasize on computing in a tightly coupled way the mechanical part of the PDs and the flow part. So basically the problem is split into two parts. In the first part, you have to find the displacement and pressure, which together satisfy a mixed system, coupled system of elliptic or parabolic PDs. The first equation resolves the conservation of linear momentum, and the second equation resolves the conservation of mass. If you have multiple phases, just water, oil, gas, etc., you also have to account for a transport phase. Second set of equations. This is a typical way. This particular, so these are basically modified transport equations, and what is strange here, unusual here, strange for people.
Peter,
Yeah.
sorry, interrupting you. I think that your sound just became a little bit worse. I don't know what was the reason.
Is it better now?
Can you repeat, please?
Is it better?
Yeah, now it's better. Yeah.
Okay. So what I'm saying is that the second equation, the second set of equations, there are two equations for oil and water. They are typical transport equations. And the third equation for gas is a little bit, looks a little bit funny, but it is actually also a transport equation. The additional terms account for the fact that gas can go into solution with oil, and it can go out of solution with oil. So this is what we in particular have done. What we build it from the ground up. As I said, we solve Bios equations. The key thing which distinguishes our simulator, for example, from Visage, is that we resolve the flow and the mechanics in a coupled way at every time step, rather than do several flow steps and compute mechanics from time to time, which is what is done in Visage. This delivers optimal accuracy without much problem in terms of it's also quite robust, and you don't have to worry about the many things which can go wrong when you usually link mechanical and flow codes. In addition to that, we also have a global local capability. We can adapt meshes in well bores, and we can couple to domain decomposition locally resolved well bores. So yeah, this is basically a description why this is the optimal way to solve coupled flow mechanics. Solids, which for example is essential when you have salt inclusions. Salts actually
Peter,
behave
sorry,
as
you started to interrupt one more time.
probably it's possible that this headset is going out of. Let me
maybe
change
because
let me
we just hear each a second word. So
yeah.
by the audio input, it will be great.
Let me change it because. Okay. I was so happy I finally found a headset which worked with Zoom, and now the battery is dead.
You were very close.
How about now? Probably better or no?
The type of sound is different, but we hear you without interruption.
So, in addition to what I described about having a monolithic coupling, locally conservative flow solution, etc., which are the essential things, we can also do nonlinear solids, which is a very typical situation in the Gulf of Mexico or West Africa fields. you probably notice why I keep talking about salt inclusions a lot. Salts actually are highly nonlinear. Their behavior is highly nonlinear. So you either have to model them as stokes fluids which flow on geological timescales, or you have to model them as highly nonlinear elastic solids. Sorry, plastic solids, which is what we have done quite a lot. The inputs to this simulator is triangulated surfaces, segway data with facies markers, salts. The properties you need are the typical mechanical properties. You need modulus, pore saturation, density. You also need initial porosity, permeability, and pore pressure. And obviously the wall trajectories. Here are some examples. The figure on the right, top right, is this is a turbidite reservoir in the Gulf of Mexico. It's part of the salt I showed earlier is part of this reservoir. Here you see part of the reservoir layer, several wells, and a fault. Turbidites are basically thin rock layers which formed after a landslide. So there is some landslide, you get some stuff, and then stuff continues to depose over the next several million years, and this landslide layer becomes a thin porous rock which may or may not have oil. So this is the top picture. The bottom picture is actually the stress, the mechanical stress in that rock near the vicinity of the wells. For example, this picture can tell you if you're about to crack the rock near the wells or not, depending on how much you inject. So what we get out in terms of primary variables of fluid pressure and mechanical displacement. And based on that, you process them to get the full strain, volumetric strain, mechanical stresses, total stresses, various stress projections on different directions, changes in porosity, permeability, etc., all the usual things. Here is one not so obvious application. This is actually the same field. The figure to the right is not from that field. This is locally resolved. Maximal and minimal stress along a wellbore trajectory. So what you will see here, if you see this graph, this tells you at each location at depth on the wellbore what is your stress. As you can see, there can be quite a difference whether you do it by simple 1D computations or you compute the data based on this kind of 3D simulations. And this can change over time as you produce the field. These curves change, which basically is relevant because sometimes you drill half of the wells initially and then the other half 10 years down the road. But when you do that, you have to know that when you start producing the reservoir, 10 years from now, you'll still be able to drill those wells that you can drill now. Or sometimes it is the reverse. You start producing the reservoir, you change the stress state to a point where something which was undrillable now becomes drillable. So these are other types of applications. There are some additional things that we have explored, but we have not gotten to the point where we can commercialize them. Here you see a device which is inside the wellbore itself. The application here was slightly different. So this is shallow wells in places with a lot of underground water, and the goal was to link the velocity in here to the background velocity of the water in that location. And the idea was that this was some device which would measure this velocity. So if you measure something here, you want to know what is the actual undisturbed water velocity. It was, if I believe correctly, it was used for monitoring dams and this kind of geological structures. These are a couple of projects, selected projects we've done in the past. I would also like to point out several other things which we explored with Bogdan over the past few months. The figures that you showed previously were done using visual rendering. They are quite sufficient for people who actually made the model. Basically, the geologists who created the model, when they see this picture, they will know immediately what is where. I mean, they know them by names. Each of these wells has name, each of these layers has name, this part has some name, this part has some other name. So when the geologist who made the model sees this picture, he will tell you how is this location called, how is this location called, how is this location called, what is the name of this fault, etc., etc., etc. However, if you see it for the first time, it is not quite clear what is the 3D structure. So using a ray tracer with shadows actually provides improvement in perception when you get to know some models. So there is something there into using ray tracers. And there is also the audio control feature that basically can make the learning curve for new employees easier, basically how to control the visualization, and how to look at things, how to find them, and so forth. So this is the same reservoir as before, visualized by ray tracing. Credit goes to Igor Romanovich, who did it in Omniverse. If you've never seen this before, it is immediately clear which part is on top, which part is on bottom. So there is an improvement there. There is another example where this is a CO2 injection simulation. Again, visualization with ray tracing and 3D by Igor. And the last thing he did was, again, this movie that I played separately. So basically, you can tell it, the sound is not there, but you can tell it to rotate, move up, move down, please find this well, please find that well. Tell me what is the pressure at this time and that well. When you have something like that, it's kind of fun and you don't have to, it makes it easier to explore the features of the software and learn where are the actual controls who can tell you the same thing. So again, credit for this thing goes to Igor. Oops. So this concludes the talk. Any questions?
Thanks for the presentation, Peter. You are just on time with the timing. So like we have like some a few minutes still for questions. I see the couple of them are in the chat. So first, Alexander Silohin asked, "Do you use something like Polygonica for 3D mesh processing?" So that's the question.
What is Polygonica and what do you mean by 3D mesh processing?
Alexander, we don't hear you. We saw that you turn on your camera and talk, but don't hear you yet.
Yeah. So I saw the mesh and it was it looks really nice. And when you talked about the need to maintain watertight and other properties, and I remember from my previous practice that I used such library like Polygonica is with a proprietary license, but it's really robust. And or you just used your own algorithms for mesh processing.
Let me show it again. Movie. So this mesh is relatively, I mean, this geological structure is relatively simple. Others can be really, really challenging when really weird configurations happen. So it was not possible to first generate initial mesh with any reasonable tool that was there like 6 or 7 years ago. So this would be the initial mesh. The triangles are too small and they basically all merge into blue. So this would be the initial mesh. Once you have an initial mesh, you have to optimize, you have to reduce the size and optimize it to get the computational mesh. We ended up doing a completely, so this is the optimization process. What you see here is the optimization process. We designed a very, very, very particular algorithm which optimizes these meshes and keeps them true to the underlying geological representation. So basically, every point of this mesh actually lies on the level set defined by some cube on the original data set. So it is not like we designed we constructed initial mesh, then we say, okay, this initial mesh is what we have. Now let's copy it and try to optimize it. We optimize with respect to the original data. And we use the usual operations, swaps, smooths, collapses, and so forth. But this is the result of algorithm which was specifically designed to optimize this type of meshes. And again, this is a nice mesh. The ones which you would have in the turbidite layers are really difficult to handle, and you have to be extremely careful not to create self-intersections. Tools which existed, they would either immediately crash, or very soon they would produce self-intersecting meshes. We haven't used polygon, but unless it was designed for that specific purpose, I don't think it will give you much.
Yeah, okay. Thank you for the answer.
There is a question about Navier-Stokes. Someone, I guess, watched movies lately. Navier-Stokes, the problem for Navier-Stokes is not how to solve it, but existence and uniqueness of solution in 3D. In 2 dimensions, in 2 spatial dimensions, the possible flow configurations are much simpler. And the existence and uniqueness of solutions was conclusively resolved by Ladizhenskaya, Babushka, and Bretzi in the 70s. So basically, they designed an inequality, and they show that this inequality is satisfied. And from this inequality, it follows that the 2-dimensional Navier-Stokes problem has a unique solution. Solution exists, and it is unique. The same has not been done in 3D. A lot of people have been trying ever since, including Ladizhenskaya herself, without any success. So this is what you would get 1 million if you can do. With regard to numerical methods, you can still solve equations in 3D, even though you don't know whether there is solution. This you can do. People do it. It is actually not the tricky part. The tricky part is what kind of discretizations to use. Because of this inequality, it's called LBB, Ladizhenskaya-Babushka-Bretzi. Because of this inequality, you have to very carefully choose how you approximate the velocity and pressure so that on the discrete level, you don't have a solution which degenerates. So it is a funny thing because the functional analysis tools which were used to prove existence and uniqueness in 2D are actually mostly used to design numerical schemes in both 2D and 3D. There is a group of people who are trying to do the reverse. Basically, they try to modify the fluids and add some vanishing terms which would imply existence and uniqueness without numerically, and from there analytically this has not been successful. What has been done with some success is to actually change the pressure, change the stress tensor. Navier-Stokes equations use a very simple linear relation between the velocity gradient and the stress. So if you introduce some kind of nonlinearity, then you can actually show existence and uniqueness. But because of that, numerics for CFD is highly complex field with a lot of subtleties that you have to take into account. For example, if you try to solve Navier-Stokes equation with linear approximation for pressure, the linear approximation for velocity, it is going to result in garbage. And the reason is that this inequality is not satisfied. So typically you have to use higher order for velocity and lower order for pressure. Or you have to put some bubbles and curious things.
So I think, Peter, you answered Bogdan's question regarding this Navier and Stokes equation, right? Bogdan also pointed out that we have some issues with mic, but sorry for that. To some extent, I think we're still it's much better than with the headphones issue, but just less louder. But still, I think we more or less hear all the things that Peter shared. But Peter, if you see the next two questions in the chat,
is there a sell to narrative for this company, or would they be competitor? I know several people here, and if you think there is a sell to, so at this point, designing a reservoir simulator which is usable by the wider public is extremely difficult, time consuming.
Now we hear you extremely bad, Peter. It become a little bit.
Okay, so what I'm saying is that to design something like Eclipse or Visage or T-Navigator is extremely difficult because you have to cover extremely wide range of cases and basically provide users with reasonable feedback to change their simulations. So we have used this simulator for consulting. Basically, we get a project, we do the computations, we present them to the client, we explain they may or may not request additional work, usually they do. And at some point, we actually give them the model with the code so that they can run it themselves and make minor changes here and there with minimal support from our end. Turning this into a mass product is very difficult and not realistic in the short run. So it is a consulting offer. Did I understand correctly that from the actual seismic data you take only the 3D geological body for further, or do you take into account the velocity or density? You take everything from the velocity, from the seismic velocity. You infer what are your mechanical properties, your density, your permeability. You infer them, you have to correlate them with well logs if you have such. Usually, originally you don't, you drill the first few wells, you correlate your material properties with what you actually drilled, then you redo the model, and then you do a second simulation for, let's say, the next 10 years of production where you utilize some data that you already got from the initial drilling. Regarding the 3D structure, the 3D structures you can usually resolve it from you use some or all of the horizons available, some or all of the inclusions available, and some or all of the faults available. It really depends what is the field and what is your interest. But each of these problems is difficult. So what we managed to solve relatively successfully was how to take various horizons and salt bodies and reservoir bodies and facies markers and quickly turn them into computational meshes. But this is just part of it. You also need to populate with properties, subscale properties, faults, blah, blah, blah. So it's part of the job.
Oh, thanks for answering, Peter. And I see the question for Stefan, do you have pre-recorded demos that are customer facing? I think right now we do have like rather, pre-recorded videos, right, Stefan, Peter? So
Yeah.
some of the videos can be shared if you
Yep.
see there's a potential prospect, and you can contact Peter directly and involve into the conversation if it's like
We
special.
have a bridge material which can be sent to clients to capture the main points.
Hope it's helpful, Stefan. So yeah, if no more questions, I would like to summarize the today's session with the both thanks for listeners who joined and basically followed the pre-complex and probably for someone new direction. Yeah, so hope you gained the insights, general insights on what is the reservoir simulation problem and what are the main challenges we are trying to solve there. And yeah, and whenever you have any more questions, ideas, feel free to share them. And I think Peter would be more than happy to collaborate and answer and work together on those challenges. Peter, thanks for you for presenting. Great presentation. And thanks for R&D Talk team who made it possible.